Hello everyone, today I'm going to show you how to create this bad boy, the finite geometric series formula, from a similar trick to what Gauss did, but for a geometric series. Now, I remind you that the geometric sequence is defined the following way. U sub n equals u1 times r to the n minus 1, and they share some of the same terms which are mentioned over here. u1 is the first term, r is the common ratio. Instead of a common difference where you add and subtract by the same thing, a common ratio is you multiplying and dividing by something. If you're dividing, you're technically multiplying by a fraction. And it's indexed to n minus 1 for counting purposes. And yeah, un is the nth term. So we're going to create a trail of terms like this over here. Let's define the sum. Let S, just to avoid, actually no, we could do it from here. So I'm going to plug in various values of n into here and generate a bunch of terms in the geometric sequence which we're going to add together. If I plug in n equals 1, I get u sub 1. If I get n equals 2, I get u sub 1, 2 minus 1, which is the same as u sub 1, oops, sorry, that's for the r. U sub 1 r, 2 minus 1, which is u sub 1 r. If I do it again, I get, for r equals 3, I get r 3 minus 1, that becomes u sub 1 r squared, and then yeah, you see the pattern, right? So I hope I can write the rest very quickly for you now. We start with u sub 1, we have u sub 1 r, u sub 1 r squared, u sub 1 r cubed, all the way up to u sub 1 r to the n minus 1, which is the most general term we have over here. Now let S be the sum of all these terms in the sequence, the geometric sequence. I'm lazy. I'm not going to put the u sub 1 r cubed there, but you'll get that it gets condensed into this omitted ... notation. Okay, very good. And just like what we did, like Gauss did with counting the sums from 1 to 100, we're going to do a little copy sort of trick, but it's going to be a subtler version of it. Instead of just creating a copy of S, we're going to create a copy of S multiplied by your general common ratio. So then Rs, if we multiply R to S, we get U1R plus U1 R squared plus U1 R cubed plus ... plus from inside here, we're going to get the same copy of this. U1 r to the n minus 1 plus u1 r to the n. Okay, and now it's better if I go and rewrite everything from top to bottom now. So I'm just going to recreate this again. S equals, trying to see, sorry, I just have to make sure that it's left to right. Okay. Bear with me to this, I have to write the equal sign a bit to the left of here. You'll see why. U1 plus U1R plus U1 R squared plus okay, this one I have to be careful just to make it look clear to you. U1 r to the n minus 1. Yep, that's the original thing we have there. Yeah, so I expand it out over here. Okay, fine. Yeah, this is just this term expanded over here. Sorry, take too long for me to go now. And now here is the magic that happens. Instead of like adding all those two terms together, we did an S and S for the arithmetic series. For the geometric series, we're going to take this RS and subtracted by s. So all this is going to be subtracted here. But what happens to most of these terms, particularly these guys over here? Because they're all the same. They get canceled. Not in the media sense, but mathematically. Boom, gone. And so you have rs minus s equals, the only remaining two terms we have left is this u sub 1 rn over here, and this u sub 1. So we get u sub 1 r to the n minus u sub 1. And now all we need to do to clear things up is do a little bit of factoring. So then factor s from here, s times r minus 1. Factor u1 from here, u1 times rn minus 1. And then divide both sides by r minus 1 to get s equals u sub 1 rn minus 1. And that is QED. You might also sometimes see this written in a different form. I'm not going to write it, I'm just going to show you how you get it right away. You would see like the 1 and the r sub n positions being reversed. That's fine, that still works, because all we did was we took this expression s and we multiplied the top and the bottom by negatives 1 over negative 1. So then s becomes u1 times negative negative becomes positive 1 minus r to the n, and then positive 1 minus r. Boom, just like that. So that's the derivation of the finite geometric series formula. Now, before we end the video, I'll do a very quick demonstration of what the infinite geometric series formula is, and the main key assumption we have to use to get that formula, which is the following. If my common ratio is bounded between 1 and minus 1, you might see the absolute value of r is less than 1. This is the same thing as negative 1. Basically, r is a common ratio that we multiply between the interval negative 1 and positive 1. Then you get that this Sn for u1 r to the n minus 1. Oh, sorry, I have to use the other form. It actually matters for this that I do this in the other form. If absolute value of r, if the common ratio is bounded between these things, limit as n goes to infinity of r to the n goes to 0. So basically, you take the limit, look at infinitely many terms, for this part of the series term, that just goes to 0, gets destroyed. So we get Sn u1 times 1 over 1 minus r. So the infinite geometric series is u1, sorry, taking me a while to write this out, infinite geometric series S infinity equals u1 over 1 minus r. And I repeat that this is really only valid for absolute value of r is less than 1. Really, the only way to kind of get intuition why this works is to plug in numbers in between the, not the unit interval, the interval negative 1 to 1, and then see that, it does happen like that way. But if you want to show it rigorously, you're going to need to know some real analysis. And for a high school course or an IB course, that is beyond the scope of the class. So that's it. I hope you enjoyed this video. In future, I might show how that rigorous trick works. Until then, thank you.